Math, math, it's all about math, 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 the wonderful world of math. Welcome to the wonderful world of math. Today we want to do some calculus stuff, areas of polar regions. So let's start by talking about how we do areas and polar coordinates all together, right? We have a region bounded by a polar curve, r equals f of theta, and we've got these radial lines, or rays, going through the angles alpha and beta. We need beta minus alpha to be less than or equal to 2 pi, but also a positive number, so that beta is further along than alpha. And f has to be positive and continuous for this to be easily defined. And in that case, we saw previously that the area of this region would be the integral from alpha to beta of 1/2 r squared d theta. Now, if we have two curves, and we want to find the area between them. If I have two positive continuous functions, f and g, where f is farther away from the pole than g, and theta, at least f is farther away than g on this interval, theta, right? As theta goes between alpha and beta, where beta and alpha, just like before, have a positive difference, and their difference is less than one full revolution. And then this region R, bounded by these two curves and these rays, will be just the difference of the integrals. The difference of R1, the area between f of theta and the pole, and R2, the area between g of theta and the pole. And when you subtract these two areas, you get the region R, right? You take away the green stuff from the blue stuff, and all of a sudden you get R. So that's the difference of these two integrals, though, which, because they both have a common factor of 1/2, and they're both integrated from alpha to beta, we can combine into one definite integral. Now that should sound an awful like what we did when we tried to find the area between two curves in rectangular coordinates a long time ago. It should, because it's very similar. So how about our first example of this? Find the area outside the curve r equals 4 minus 3 cosine theta, and inside r equals 2 plus cosine theta. The first thing we want to do is we'd like to graph these, so we have an idea what's inside what and what's outside what. And once we do that, we're generally going to have to look for intersections, if any exist. So first of all, let's make tables for each of these things. We're going to start by plugging in easy stuff, and if we need more points, we can plug in more points. Now this is cosine, so we'd like to plug in quadrantal angles and anything with a reference angle of pi over 3. We were also going to use symmetry, because this has a cosine in it and no sines. We're going to suspect that perhaps this is symmetric about the polar axis, the old x-axis, the line theta equals 0. And they both will be, and you can show that. We can show that this equation is symmetric about theta equals 0 by taking a point and saying that this guy over here must also be a solution of this equation, so we can substitute negative theta in for theta, and if it still equals r, then it's symmetric about the old x-axis. This is our symmetry test, and you do the same thing for r equals 4 minus cosine theta. But it's going to work out, which means that we really only need to plug in thetas from quadrants 1 and 2, and quadrants 3 and 4 will be mirrors of those. So we're going to plug in 0 and pi over 3, and the quadrantal angles and everything with the pi over 3 reference angle. And then this is enough for us to get a pretty good idea of what's going on, and then we can fill in the, like we said, third and fourth quadrants from symmetry. Now, when I plug in 0, this is 2 plus cosine of 0, that's 2 plus 1, there's 3. When I plug in pi over 3, that's cosine of pi over 3 is 1/2. 2 plus 1/2. Well, we'll just say 2.5 to make it easier. 5.5 or 2.5. When I plug in pi halves, cosine of pi halves is 0, so that's 2 plus 0, 2. When I plug in 2 pi over 3. Cosine is negative in the second quadrant. This is going to be 2 plus negative 1/2, or 2 minus 1/2. 4 halves minus 1/2 is 3 halves, or 1.5. And then cosine of pi is going to be negative 1, so 2 plus negative 1, 2 minus 1 is 1. So here we have those 5 points. We've got 3, 0, 5 halves, pi thirds. We've got 2, pi halves, 3 halves, 2 pi thirds, and 1, pi. And we're going to get their mirrors in the third and fourth quadrants from symmetry. We're going to have down here at 4 pi over 3, 1.5. And we're going to have 2, 3 pi over 2. And we're going to have at 5 pi over 3, we're going to have 5 halves again. And this connects to form a nice curve. And it looks roughly like this. Now for the other graph, we're going to plug in the same points to start with. Right? We're going to plug in all the things with reference angle pi over 3 and all the quadrantal angles, except that we really only have to do 0 through pi because of that same symmetry, which you should also show. Right? Now 0, when we plug in 0, cosine of 0 is 1, so 4 minus 3 times 1, or 4 minus 3. When I plug in pi over 3 makes cosine 1/2, so that becomes 4 minus 3 times 1/2, or 4 minus 3 halves. 8 halves minus 3 halves is 5 halves, or 2.5. Interesting. By complete happenstance and coincidence, we have managed to find an intersection point, 2.5, 3, pi over 3. Now, let's forget about that for a second. We've got more stuff to do. Pi over 2 makes cosine 0, so this is 4 minus 0, 4. This is going to make this negative 1/2. So 4 minus 3 times negative 1/2 is 4 plus 3 halves. 8 halves plus 3 halves is 11 halves, or 5.5. And then when we plug in pi, this is just going to be 4 plus 3. So 7. So we'll get these points, and we're going to get the other ones from symmetry. We're going to get the mirror of this point down here at 4 pi over 3. You got 1, 2, 3, 4, 5.5, 4 pi over 3. And at 3 pi over 2, you're going to have exactly 1, 2, 3, 4. And of course, we've got this other intersection point here. Now, you may want some more points, so feel free to go back into the first quadrant and the second quadrant and plot a few more points to get a better grasp for the shape. So go ahead and try to compute those, and we'll check our work together in 3, 2, 1, and there we are. These are the r's that go with these thetas, and this is what it looks like when we plot those guys and their mirror images. And we get a curve that actually looks pretty nice. Go us! Now we've got our plane region broken into 4 pieces, A and B and C, and of course D here. 3 that are remotely possible. If we said inside something and outside something else, D is not going to really have a shot at it. But based on this, which of the 3 areas, A, B, or C, do we want? Area outside r equals 4 minus 3 cosine theta. That was the blue one. And inside, the green one, r equals 2 plus cosine theta. Outside the blue one means that I'm not going to pick A. That's inside the blue one. B is also inside the blue one, so if it's inside something and outside the blue one, then it's got to be C. This is what we would like to find the area of. Now, we'd like to find the area as theta goes from here, where these 2 curves intersect and the green one becomes further away from the pole, to here, where these curves intersect and the green one stops being the one further away from the pole. So we would like to find those points of intersection. Now, we kind of found them magically already, but let's find them analytically, just so that we know what to do even when it's not super magical and easy. To find intersections of 2 curves, typically we had 2 methods, the elimination method and the substitution method, and if this stuff wasn't linear, we were supposed to generally favor the substitution method. That is a good idea. So here you have r equals 2 plus cosine theta, and r equals 4 minus 3 cosine theta. Now if these are supposed to be the same point on both curves, r comma theta here is supposed to be the same r and theta here. That means that this r and this r, if it's a point on both curves, must be the same r with the same theta. So you can set r equal to r, or things that are equal to r, equal to each other. You get this equation, and then we solve for at least cosine theta to start with. We're going to add 3 cosine theta to both sides, and then we're going to subtract 2 from both sides. And what we end up with is something that's got one term on each side. Divide both sides by the coefficient of cosine to find we want cosine theta to be 1/2. Now, for which angles between 0 and 2 pi is theta equal to 1/2? That's pi over 3 and 5 pi over 3. Right, these are the two standards. You could also pick negative pi over 3 and negative 5 pi over 3 and 7 pi over 3, etc. But these are the two best. We already know from having plugged this into both of the curves, we know the r value. Okay, now let's head on over to our integral. The area of this region is going to be 1/2 the integral from alpha to beta of f of theta squared minus g of theta squared d theta. Right, this is what we want. Now we just say, what's f, what's g, where's alpha, where's beta? Now we can go from here to here, and that'll do it, except that we don't want to say 5 pi over 3 to pi over 3. That's not in one go. So if you're going to do it that way, you got to change your perspective on this 5 pi over 3 and make it say negative pi over 3. It's equivalent, but now you can go from here to here in one go. That's pretty nice. You know what's nicer? Noticing that this thing is symmetric about the line theta equals 0, instead of going from here to here, we can take the first quadrant portion, 0 to pi over 3, and just double it. So instead of doing this from negative pi over 3 to pi over 3, we can do 2 times the integral from 0 to pi over 3, using symmetry. Now which of these two curves is our f and which one is g? Now the further away curve from the pole is going to be the green one. That was 2 plus cosine theta. So we multiply this 2 times this 1/2, and we replace f with 2 plus cosine theta squared minus, replacing g now with the other one, 4 minus 3 cosine theta, also parentheses squared, d theta. Now you're going to have to FOIL both of these. 2 squared plus 2 times cosine theta times 2 times cosine theta squared. And that's great. And now on the other one, we've got 4 squared minus 2 times 4 times 3 cosine theta, so that's 24 cosine theta, and then plus 9 cosine squared theta. Okay, cool. And now we're going to distribute this minus sign and combine like terms. After distributing the minus sign, we say 4 and the negative 16 are like terms. 4 cosine theta, 24 cosine theta, the same sign, so this is going to be 28 cosine theta. And then we've got 1 cosine squared minus 9 cosine squared minus 8 cosine squared theta. Now, if you've done a lot of integrals of cosine squared lately, you have a pretty good idea that we're going to separate these easy guys apart from this, which is going to need an identity to take care of. The identity we want is called one of the power reduction formulas. It says cosine squared theta equals 1 plus cosine 2 theta all over 2. And this comes from the cosine double angle identities. So we've separated this into the integral of these two guys, and we've separated this one over here into the integral of 1 plus cosine 2 theta all over 2. Now let's go ahead and integrate this stuff and take care of it while we're working on making this better. The integral of cosine theta and sine theta. So this becomes 28 sine theta, and the integral of 12 d theta would be 12 theta. And we're going to evaluate this from 0 to pi over 3, and we'll do that stuff on the next step. Now here, we've got this 8 in front, and we've got this 1/2, or this 2 in the denominator. You bring it out in front. 8 halves becomes 4. Now, we like to get all that stuff out of the way so that we can take care of this. This is some pretty standard stuff, but this is cosine of 2 theta. In order to properly do this, and to make sure that we're keeping track of everything, we're going to use u substitution, where u equals the inside of the cosine, it's 2 theta, so that du equals 2 d theta. And the reason that we wanted to do this substitution, because this du is not equal to d theta, it's equal to 2 d theta. So usually what we do there is divide both sides by 2 and get 1/2 du equals d theta. This is a definite integral though, so you want to do u of 0, well that's 2 times 0 is 0. And u of pi over 3, that's 2 times pi over 3 or 2 pi over 3. So we're going to replace the limits of integration with these guys, and we're going to replace 2 theta with u and d theta with 1/2 du. So after our substitution, we should have this. Now we can go ahead and plug these guys in here and move this factor of 1/2 out front also. 28 times sine of pi over 3 minus 12 times pi over 3, all minus 28 times sine of 0 minus 12 times 0. And I'm going to go erase this because we don't have enough room for both, and because sine of 0 is 0, and 12 times 0 is also 0. So this, we wrote it, but it's 0. So now we can continue evaluating this stuff, and we're going to find the antiderivatives of these guys with respect to u. Sine of pi over 3 is root 3 over 2, and 12 times pi over 3 reduces to 4 pi. Now the antiderivative of 1 with respect to u is u, and this cosine stuff it just becomes sine. Right? The antiderivative of cosine u is sine u, from 0 to 2 pi over 3 now. Reducing this, common factor of 2 becomes 14 radical 3, and now we're going to plug in 2 pi over 3 and 0, and you get 0 plus sine 0, and that's all going to be 0 again. Sine of 2 pi over 3 is the same as sine of pi over 3. They're both root 3 over 2. So we're going to distribute this and combine like radicals or like terms. 14 radical 3 minus radical 3 is 13 root 3. And as far as this stuff goes, we get a common denominator. 4 pi times 3 over 3 is 12 pi over 3, which is sort of how we got that in the first place, right? Now, 12 pi over 3 minus 4 pi over 3 is 16 pi over 3. Ta-da! Now, because this example took so gosh darn long, we're going to save the second example of the area between two curves for next time, and we'll leave you with the dinosaur of the day, Oryctodromeus, the digging runner. Runs a hole and digs away, I guess. I don't know. I just thought it was a funny sounding dinosaur name. This has been a Badger Bear production of the wonderful world of math. Now, if you need me, I'll be at the cafe having a sandwich. Ciao!